to begin. Спасибо. So we'd like to start by thanking Steklov Institute and Yuri for a nice invitation to speak here. It is my second visit to St. Petersburg, and it's a very beautiful city, amazing history, and just very happy to be here. So today's talk perhaps will be called multimedia. We might have some, well, we'll see if everything succeeds. We'll have multimedia talk. And it is mainly about, the general idea is we start with function f, z, and I won't use z, I'll usually use s. And this will be a complex variable. First thing I learned when I started working a little bit in analytic number theory, it's no more z, but s sigma plus rt, traditional notation. And such functions are difficult to graph, impossible. Of course, you need four-dimensional graph. But it is possible, perhaps you could plot the modulus of f of z, f of s, and perhaps you can make some graph of this. You could even plot it on horizontal lines as of sigma along the horizontal line. You could also consider along vertical lines. You can get some picture that way. That's a possible case when such a graph is monotone and it's very simple to function. So modulus, let's say f of s, is monotone. And by that we mean strictly monotone, along, say, horizontal line, possibly along vertical line. In particular, since this is always at least 0, if it's monotone, then that would imply that there are no zeros along that line. You can't descend below 0 if it's monotone. So this would imply f of s not equal to 0 on given volume. So we can fix t, or we can fix sigma. So that's general theme, and we will study that for certain functions. The main functions we look at today, well, I might give one or two very simple examples with other functions, but we will look at gamma function and zeta function, Riemann zeta function, and associated functions, the zeta function. I'll just write down the names of those functions. We will define them very soon. Excuse me. So gamma, zeta, the Riemann psi function, and Euler Dedekind function called A. We will define those. So I will use the projector now for this first slide. So let's see. So it's I should say one little thing. I was going to talk once in Canada. One of my colleagues there in Montreal, Jacques Bernays, was giving a talk, and he was doing the system that people often use, with covering part of the slide. And then he said, "Don't you hate it when people use this system? It's like striptease with slides." So, sorry I'm doing it, but usually I won't. Anyway, this is very famous curve. So it's the modulus of Riemann zeta function. We fix sigma as 1/2. So this is exactly along what's called the critical line in the complex plane. The real part is 1/2. And t is going from 0 to 100. So this is a very famous curve, very horrible curve to look at, very irregular. And the 0 is the most famous part. This graph is not exactly right. This is 0 here is 0. This is at 14.1 approximately, about 21 and about 26. These are the famous zeros of Riemann zeta function. So looking at it along this vertical line, very, very complicated. If we tried other vertical lines, for example, if I changed 1/2 to 0.6, you would get very similar curves, but it would no longer come all the way down. It would just be coming close to the real line, because there are no zeros in that region. But the curve would be very similar. So what about if we look at it along horizontal line? And this was the thing I was looking at with my co-author here was Philip Seidel. I will write his name later. So let's see does that show up? Maybe like that. I have a little, put it over there. Small, heavy objects, then we can see the whole slide. Maybe just this one. Yeah. Okay, so let's look at it in horizontal direction. And we fix the value of t, call it t0. So in this case, we're just looking at sigma going from 0 to 1, what's called the critical strip. But we can also talk about it further. Of course, one thing, perhaps I should have defined the zeta function right away. So one easy definition would be zeta of s is simply summation 1 over n to the s. This is the so-called Dirichlet series for it. And it won't be a general conversion, but if sigma is greater than 1, that converges. So one thing you can see right away from that, as sigma approaches infinity, as we go to the right, the limit will simply be 1. All the higher terms just go to 0 as sigma goes to infinity. So the limit of zeta of s as sigma goes to infinity is always equal to 1. Okay, so let's look at these curves. I'll take one of these. So here is t equals 17, and it's just a very simple curve, monotone decreasing. Of course, if we extend it to the right, all of these curves must be asymptotic to 1. So this is 1.8. Eventually, it will just be asymptotic to 1. Similarly, at this one, 24.5, this is close to a 0 of Riemann zeta function, and the next one is at a 0. T is 25.011, very close to an actual 0 of zeta. And it comes down to 0. But in any case, we see that it behaves pretty simply in horizontal direction. In particular, up to 1/2, it's always monotone decreasing. Monotone decreasing, monotone decreasing. And that's one of the main theorems we will talk about today. If we extend this further, then as I said, this will be asymptotic to 1. So it's going to come back up and approach 1. It will not be asymptotic in that direction, although it approaches 1, it goes oscillating about it. If we extend it to the left, though, at that time when I did this work with Philip Sadat, we were mainly just interested in critical strip. So, if we extend to the left, in fact, it's always monotone. From 0 left, we have actually proved that it's monotone, and I hope I can show you the proof or outline it today. So we know that it's monotone to the left. Okay, so I hope that shows that in monotone direction, it somehow seems simpler. One other thing that we proved with Philip Sadat at that time is a comparison. Perhaps this is the best one to look at. If we take any value of t, on any value of t, and you go back, take the modulus, let's say we go back to this point, and then we go to the same point here, we get a smaller value. So what it says is the modulus is always larger on this side than this. Here it's quite obvious. Here it's pretty obvious. Here it's pretty obvious. If I look at, say, 0.4, it says the modulus of 0.4 should be bigger than the modulus of 0.6. A little hard to see, but if I go back to 0.2, the modulus here is obviously bigger than modulus at 0.8. So the theorem we proved was that the modulus of zeta of 1/2 minus delta plus it is greater than or equal to modulus of zeta of 1/2 plus delta plus it. So it's point symmetrical with the critical line. The modulus on the left side is greater than that on the right side. This theorem was known earlier. A mathematician in the University of Tennessee in Spira had also proved this back in the 60s. But in the work we did with Philip Sadat, we actually took the ratio of these two and we did very close values. So we did a lot more than just showing this theorem. We compute the ratio of the two, very close lower bound and upper bound. And I should just say one other thing. If we could get rid of the just changes to the strictly greater, that's Riemann hypothesis. If this is greater than or equal to the strictly greater, you prove Riemann hypothesis. So it's
so you are on the brink of proving it.
Well, it looks like a very close approximation to it. But close can be very far. It's such a difficult problem, so you don't know if you're close, you still might be very far. Okay, so now let's see what I should.
By the way, how do you deduce the Riemann hypothesis from this strict inequality?
Okay.
Is it simple?
Yes, it's quite simple.
Warum liegt es Blut?
So So let me see if I remember. There's something called functional equation of Riemann zeta function, which relates zeta of s to zeta of 1 minus s. In particular, if one of these is 0, the other will be 0 for functional equation. And what that implies is that the zeros will either be on critical line. If there are any off of critical line, they must occur with its conjugate. This would be s. This is conjugate of s. This would be 1 minus s. And this would be conjugate of 1 minus s. So they would occur in quadruples, rectangles. So of course, if this is strictly greater than this, then you can't have a pair of zeros off critical line. So that's how you prove it. The zeros must occur in, if there's any off the critical line, they will occur in rectangles in 4 or quadruples. It's okay? Good. Good. So what I'd like to come to then to measure this monotonicity, we will be looking quite a lot at the logarithmic derivative. So quite often I look at f of s over f of s. That will be very important for what we study today. And in fact, I'd like to tell you one lemma. So lemma says the following. So first of all, we have f holomorphic in subdomain D. D will be an open domain. And I have a point S in D. And I'll also assume that f of s not equal to 0. Then we're interested in how fast the modulus is changing, let's say along a horizontal line. So that asks, can we measure the rate of change of the modulus with respect to sigma? We'd like to know the rate of change, and very simple formula for that. It equals 1 over modulus f of s times the real part of the logarithmic derivative. So, where does this come from? Well, you could give this as an exercise in complex analysis in first chapter. Have students prove it. It's very easy proof. I don't know how many things I should prove, but maybe it's worth to do that one. I think it just takes 2 minutes. But like I said, if I ever write a book in complex analysis, this will be exercise in chapter 1. So here's how you would prove it. The modulus of f of s squared, well, I better, let me just introduce some notation. So usual notation, it's equal to u plus iv. We have holomorphic function, we have the real part, the I part. U is a function of sigma t plus iv of sigma t. And one other small thing I will do to make this proof easier to write. If I take the derivative, let's say du d sigma, let me just write that as u sub sigma h. It's frequently written that way for partial derivatives. It will be a little easier to write. So f of s squared is simply equal to u squared plus v squared. and therefore differentiating this to take the partial derivative with respect to sigma, I get twice f of s partial f of s sigma equals 2u sigma plus 2v v sigma. So I can get rid of the 2's. And that, I'm trying to prove this little lemma. So that pretty well computes the left side. In fact, the f of s is up here. Let's compute the real part of f prime of s over f of s. So what is f prime of s? Well, it's possible to differentiate a holomorphic function in several ways. You can approach your point along any path, but let's approach it just along the horizontal path. Then one formula for the derivative is just u sigma plus v sigma. We can just take the sigma derivative, that will give us f prime of s.
Yeah.
So if
I times v sigma.
I times, yes, thank you. Exactly. So if I take f prime of s over f of s, I have u sigma divided by u plus iv, and usual way, we multiply numerator and denominator by u minus iv. So I get u squared plus v squared, which is the norm squared. And what do I get in numerator? Well, let's do some arithmetic in our heads since there's no room. So I'm taking this times the conjugate of this. I get u sigma times u, or u sigma. And I will get plus dv sigma. And then I'll get an odd part, which I don't care. Of course, I want the real part of that. So, real part of this logarithmic derivative is simply u sigma over f of s squared. And that is exactly what we have here. So just setting this part equal to this, you get the money. So very elementary. And as a parallelism for that lemma, we're interested in the monotone property, so we'd like to know when this partial derivative is positive or negative. Maybe we'll look at the positive case. So when would this be increasing? Of course, this has the same sign as this, as the real part of the logarithmic derivative. So we can get the following corollary, that if, let's say, the real part of f prime over f is greater than 0 in some domain V, then the modulus of f is monotone increasing along any horizontal line. Let's say t equals t0 inside that domain. And in particular, it can't be 0. So obviously this implies f of s not equal to 0 in that domain. Good. And of course, there's similar one for negative. It will be monotone decreasing, very similar. So one thing that I only noticed a few months ago, actually. It's very simple a theorem. If you want to get the rate of increase in the t direction, in the vertical direction, you have exactly the same thing with imaginary part. Maybe there was a negative sign, I don't remember, but just get the same number with the imaginary part you've been measuring in the vertical direction. Good, so this lemma is the main tool that we will use to prove that something is monotone. I can get rid of this now. Okay, I hope that can work. Maybe I show you now some more slides. Yes. First slide I wanted to show just had some references. So in fact, much of the work I'm talking about is joint work with Yuri and also Philip Sada. So here are references. Let's see if I can put old ones here. So the first one is a very excellent book. At least I think it's a really nice book. I managed to learn something from this book by Edwards. Second is the paper I mentioned with Philip Seida. There's a recent paper by Sandel Dumitrescu related to the function psi. And we're actually going to maybe give a proof of that result, monotonicity for psi. There's the older paper by Spear that I mentioned. There's a paper for the gamma function with my colleague from Mumbai, Gopala Srinivasan. And we showed the monotonicity for the gamma function, for a theorem about monotonicity, which I will show you soon. And then there's a new paper that we have on archive, just maybe 1 week ago. We put on archive, and this is the paper with Yuri and Philip. So this is monotonicity for the Riemann function, the psi function, and the eta function. So those are some of the references. I could recommend one other reference. I didn't have room to write it down here, but it's a paper also with Philip Sayat and with Elena Grudyantseva from Moscow, some of you might know her. She visited probably for a while, so I'll just mention and it's in a journal called Monotonicity, which you can find. You can download this just by going to their website. And I think it was number 9. If you just go to the website, you can download that. So I should have the reference here somewhere. Let's see.
I think there are references somewhere here.
Pardon?
There are references in this paper.
Yes, it's referred to in this method too.
Anyway, you can find them by Google.
Yeah.
From the names and the name
You
of
can
the
also
journal.
find this. But I think I can find it too. So Morphismos 9, 2005. Okay. And I think it's a very nice expository paper about Riemann zeta function. I will recommend it. Okay, so now I think we have a few more slides to do. Then I won't use them again. Next slide, of course, the Riemann zeta function. One of the most interesting thing perhaps is to find the zeros. So here's a picture of some of the zeros. See how much we get there? Zeros of zeta. Yeah, that's good enough. So what we can see here, there are the so-called trivial zeros. And by the way, much of this along this axis, the real axis, it was already studied in St. Petersburg by Euler. So Euler already knew that it's 0 and -2, -4, -6, all negative even numbers. Euler understood it very well along the real axis. And I've heard talks of Euler where he explained Euler's methods very clearly. So then it was Riemann, of course, who extended it to a function of a complex variable. So now you look at it in the complex plane. And one of the first things he could prove is his functional equation that showed that any other zeros, these are the so-called trivial zeros, they're not the interesting zeros, the non-trivial zeros must all lie in this critical strip, real part between 0 and 1. And here are some of the non-trivial zeros. I believe that Riemann actually had computed the first 3. Then later, like year about 1900, 1905 prime, computing the first 15. So perhaps the ones you see in this picture. And now I think it's the first 5 or 10 billion have been computed. They all lie on this line. So of course, famous Riemann hypothesis. All non-trivial zeros of zeta lie on the critical line. So, next slide. If I have this organized, we should have a look at Riemann. So, I should have had a picture of Euler too, but I didn't get a chance to take one. Anyway, he wrote his famous paper in the year 1859. He received his PhD somewhat before that. At Göttingen, he became a professor and did this work. How did he get interested in number theory? His work beforehand was in, of course, geometry, complex analysis. Well, it's very good conjecture that he was interested in number theory because of a visitor from St. Petersburg, namely Chebyshev, who visited Berlin and had many discussions with Dedekind, who was, I believe, a teacher of Riemann. So here's, this is a photocopy from the book by Edwards. This is Riemann's own writing, and part of it is magnified. I think mathematical history is very, very interesting. So here's the way that Riemann did things. I hate to think of what he would have done today with modern computers, including things like this. And he was writing a letter to Chebyshev. So it might be a bit hard to read that, but in the book they magnified it. So this little section is magnified. And what it is saying is there, Chebyshev, Mitli, der Akademie zu St. Petersburg, hochachtungsvoll der Verfasser. He was a member of the Academy of St. Petersburg with great respect, the author. I don't know if he ever wrote the letter to Chebyshev or not. I don't think so, but he was starting to write a letter to Chebyshev. So obviously he knew of Chebyshev's work, which was related to the prime number theorem, and that was the main motivation for working on Riemann zeta function. So
By the way, where is the relation of what you are speaking about to number theory?
It's a very good question.
It's only complex analysis, isn't it? So far.
Well, yes. What I should say, though, is that what Riemann showed, and I won't be able to show this in this talk, but what Riemann showed is that the distribution of these zeros along that in that critical strip, they're very closely related to distribution of prime numbers. And that this was one approach to proving the prime number theorem. And it eventually succeeded. By 1895, people knew more than what Riemann knew, and they were able to prove the prime number theorem. Of course, that is Adamar and de la Belle-Poussin. Independently, 1895 succeeded in proving the prime number theorem, but it is very closely related to distribution of the zeros. In fact, I'll say one small thing about that to show you, give you some idea how powerful Riemann hypothesis is. Let me draw this picture. Complex plane. Here's 0, 1, and here's your critical strip. So Riemann already proved that 0, for any non-trivial 0, we have trivial zeros here. Any non-trivial one 0 less than or equal to sigma, less than or equal to 1. The crux of the prime number theorem and the way they succeeded in proving it was by improving this result. So this is Riemann. And Adamar, so I'll write down the full name, but de la Belle-Poussin, and the L, this one. What they succeeded in doing, and I like to sometimes say that I think probably the greatest achievement of 19th century mathematics was the prime number theorem. This group by Adamar and de la Belle-Poussin.
It was discovered by Chebyshev and later proved by Adamar and Poussin.
Yes.
That was Arnold taught.
But it was done before Chebyshev. I mean, Gauss already conjectured this. One version of it when he was only...
According to Arnold, Chebyshev made the most crucial step.
Oh yes, this is definitely true. Yes. That is why Riemann wanted to write to it. That's definitely true. But the theorem itself was stated before Chebyshev. Even Gauss conjectured this theorem when he was a teenager. So, the prime number theorem is equivalent to reducing the critical strip by removing its boundary. That is the greatest achievement of 19th century mathematics, removing the boundary of the critical strip. That's equivalent to prime number theorem. So that also gives you some idea of how powerful Riemann hypothesis is. It says you don't just do this, but Riemann hypothesis says sigma equals 1/2. So the Riemann zeta function and its zeros are very closely related to the distribution of primes. I don't think I can go into that in this talk. I want to talk about some other things. But I hope that answers a little bit of the question you said. It's okay? No. It's not obvious what the relation is.
Well, we know something.
Mm-hmm. So, I like to show a couple of more slides. Gamma function. So these slides are connected to monotonicity, and I think I have already explained how it can be interesting from certain points of view. Here is the gamma function. And get this. So this is the modulus of the gamma function. The first amazing thing about this picture, it was done in the 1930s by two German mathematicians, Janka and Ende. They wrote a book on tables of complex functions. One of the very first ones is the gamma function. So this is a picture of the modulus of the gamma function. They did all this years before we had anything like computer graphics. And they have pictures like this for all famous functions, Bessel functions, you name it. So amazing work they did. And so the gamma function, of course, it just generalizes the factorial function, again, discovered by Euler. And along t equals 0, along the real axis, this would be along the real axis, here is just the factorial. So gamma of n plus 1 would be n factorial at integers. Nicely monotone increasing, but horribly badly behaved along the real axis. You have poles at every negative integer. 0, minus 1, minus 2, all these poles. So the theorem that I proved with Gopalov is that actually if you get away from the real axis, it becomes monotone. So if we look at t equals 2.5 or minus 2.5, it's symmetric. You can reflect conjugation, doesn't change the modulus. You can, well, it looks like this curve is monotone increasing. And in fact, we proved it. So once you get to within distance 5/4, even a little bit less, away from the real axis, the modulus of gamma is monotone increasing. I think that we might actually be able to prove that today, but well, let's see how much patience we have. So now I'd like to show you a couple of other slides, which I think are interesting in themselves, because, okay, here we have, then I'm going to mostly use Blackboard. First one, but this can show you that by studying horizontal monotonicity, you can also sometimes learn some surprising things about vertical structure. So the first picture we already saw. This is the modulus of the Riemann zeta function along the critical line. The top is the command in maple. So it's the absolute value of zeta, 1/2 plus it from 0 to 50. It's the same picture we had before. Next one will be its derivative. So this is when it says zeta of 1. Zeta of 1 comma 1 means the first derivative. Again in the same region, and it's completely irregular. One fun thing I can do, let's see, with these projections is look at the two together. So you can see zeta and its first derivative. Like most functions, they're not too related. Some relation between any function is derivative, but very different curves. Now I want to look at the logarithmic derivative. That will be inverse. Of course, if I'm dividing zeta prime by zeta, zeta has many zeros here. So the logarithmic derivative goes off to infinity. Its modulus will become infinite. That sounds very bad. So let's just look at the real part of the logarithmic derivative. The next picture will show two curves. The real part of the logarithmic derivative along critical line and minus half the log of t over 2 pi. Very simple curve. So, although those last two functions were so complicated, you divide one by the other, get the logarithmic derivative, look at the real part. and it's absolutely simple curve. This is zeta prime over zeta, and this is minus half log of t over 2 pi. Well, we only see one curve, so it looks like they're equal. They're not equal. Let me show you one other slide here. I'm going to look at this now for slightly smaller values of t. The same curve, but slightly smaller values of t. And you can see that they're not equal. I don't remember which is which, but one is the real part, one is the logarithm. As t, by the time t is 3, you already cannot tell them apart. The difference is exponentially small. So for all practical purposes, they become equal once t gets reasonably large. So I think that's somewhat remarkable. And, we take these two complicated curves, divide one by the other, look at the real part, and it's very simple curve, up to this tiny factor. Okay, I think now I don't need the projector for some time. Can I turn it off? I'll turn it on again. There's one last slide. Now I should just use the blackboard. Okay. So as I already said, we're going to look at these functions, and maybe I should find them. So the gamma function, integral from 0 to infinity, defined by Euler, x to the s minus 1 over e to the x dx. And this will not always be convergent, but as long as sigma is greater than 0, the real part of s, this defines it quite nicely. So now, let me just see my plan here. One function that we'll talk about quite a bit is called the Dedekind function. Let me just squeeze that in here. It's simply logarithmic derivative of gamma. So I won't say much about that now, but it's gamma prime over gamma of s, and it's called Dedekind. So, what about the zeta function? Well, we've already defined zeta function, but I'd like to show you another way you can define it. If I take zeta of s times gamma of s, I get an integral that's almost the same as this one. Almost the same integral, but it becomes a zeta function times gamma function. Gamma function, by the way, is never 0 anywhere in a complex plane. It's just simply non-zero, and obviously this becomes much more complicated. This will converge for sigma greater than 1. It will not diverge. It will diverge for sigma is less than 1. Okay, the psi function is defined by Riemann. And copy this one down. Remember exactly. Times gamma. So that is the definition of the Riemann psi function. And one of its nice properties, we said that the zeta has a functional equation. Riemann realized that by modifying the zeta slightly in this way, you get a function with even nicer properties. So we're going to use this function. the two stars here. I will try and leave that on the board. Come back to it. So this has two nice properties. Psi is holomorphic in all of C. In other words, it's an entire function. The zeta function has one pole. When s equals 1, you've eliminated that by this multiplication. And you get a function that's now holomorphic. And it has a very simple functional equation. So it's actually become symmetric in the critical line. Last function we talk about is called the Euler Dedekind beta function. And it can be given by alternating Dirichlet series. The zeta function, here it is. If I just alternate the signs, I get this function. So it's 1 minus 1 over 2 to the s plus 1 over 3 to the s minus 1 over 4 to the s. So very much like the zeta function with alternating signs. One slight advantage, and this was used very much by Euler. Of course, Euler only considered when s is a real number. But this one, the zeta Dirichlet series converges to sigma greater than 1. This actually converges to sigma greater than 0. It will be conditionally convergent between 0 and 1, but still convergent. And you can also write this eta of s is 1 minus 2 to the 1 minus s times zeta of s. It's fairly easy to prove this. I hope I got that right. 2 to the 1 minus s, yeah. And I will call this equation, I'd like to use this equation, call that one star. Okay, so those are the functions we want to look at. And for all of these functions, they're all what you could call a real type complex function, meaning that f of s bar, f of s conjugate, simply means these functions apply to a real number, give you a real number, and this is for all. Any of the above functions satisfy that division is symmetric with respect to the real axis. One other item that we will need are the Bernoulli numbers. And perhaps I won't write down the definition. I know most people have seen it at some point. Again, the big connection with St. Petersburg, because Jakob Bernoulli was the one who told Euler that he should come to St. Petersburg. And I think he got special permission for him. He was rented the academy. In, I believe it was the Department of Medicine, is that right?
Physiology.
Pardon?
Physiology.
Physiology, yes. So I'll just write down a few. P0 is 1, P1 is 1 half, or is it minus a half? I guess it's minus a half. Yeah. P2 equals 1/6. And after that, all odd numbers are 0. P odd equals 0 once it has P1. And P4 will be 1/30th, and so on. Okay, we don't need too much. So Bernoulli numbers come out quite a bit when we study these functions. Right, so what I'd like to do next is look at first this function, psi, the monotonicity of psi was studied by one of the papers I mentioned, Steklov, and they showed that it is monotone. There are some results in literature even before that anticipate that, but they didn't state it so directly, even going back to the paper of Euler. So I'd like to prove the monotonicity, show you how simple it is from our little lemma here. This result of Steklov and Trisco, it's about a 5-line proof. So maybe I'm talking almost 1 hour. Let me show you that little proof, and then if you want, we can take a short break. I don't know how long you'd like to go. Let's at least see how we get monotonicity for psi. And in fact, maybe what I'll mention, you should leave these things here.
You mean monotonicity of the modulus on the horizontal and vertical lines?
Along horizontal lines.
Horizontal, okay.
Yes. In fact, what we will prove if we look at this functional equation for psi, the equation that I wrote here, it is symmetric. So we're interested to show that the modulus of psi is decreasing to the left of critical line, but that would be equivalent to showing that it's increasing to the right, because it's symmetric. So here's the picture. The modulus of psi should look something like that. So this is the modulus, let's say, psi of sigma plus I T0. So of course, because of this symmetry property, increasing here is equivalent to decreasing here. So the theorem of Steklov and Trisco says that the modulus of psi of s, we fix T0. So the modulus of, psi of sigma plus I T0 is monotone decreasing for sigma less than 0, and also monotone decreasing for a slightly bigger region, sigma less than 1/2. This is equivalent to Riemann hypothesis. So the theorem says it's decreasing up to 0. If you want to extend that further to a slightly larger region up to critical line, that will be equivalent to Riemann hypothesis. And what I claim is using this little result, this thing, we can prove it almost trivially. Now we need to use one other thing.
Peter,
So,
stop for a second. We need to change the cassette here.
well, maybe it's good if you said that.
No.
We're going 1 hour. We can take a short break. Okay, you tell me what. I start again. So we come back to this theorem. And it should maybe say monotone decreasing in sigma. So we're fixing T0 and studying the modulus along horizontal curve. Okay, well let me show you a very short proof. We saw that this function psi is holomorphic in the entire complex plane. That means it's an entire function. The theory of infinite products for entire functions was developed by Weierstrass in about 1870. And I think that if Riemann had lived a little longer, he died in about 1860, and shortly after he wrote his famous paper, he would have been able to solve the prime number theory, because the missing step was to find a product expansion for psi using Weierstrass's theory. This is done by Hadamard. So, Hadamard, I guess also I should mention Fontanka. So any entire function can be expanded in a very nice way as an infinite product. It depends on the zeros, this infinite product. And I won't go through all of this, but let me just show you that if you take this expansion and take its logarithmic derivative, you get very, very simple formula. So this implies that psi prime s over psi of s. By the way, one thing I forgot to say, the gamma function is never zero. This is never zero. This can only be 0 or 1. So it has exactly the same zeros as the zeta function, the non-trivial zeros. So the zeros of psi are exactly the non-trivial zeros of zeta. It has no other zeros. The trivial zeros of zeta are no longer there when you take psi, because of the poles of gamma. So the zeros of psi are basically the same as the zeros of zeta along the critical line. And the Weierstrass product expansion is in terms of the zeros of the function. We take the logarithmic derivative of that product and you get a sum. And the sum is extremely simple. It's just summation 1 over s minus rho. What is rho? So s is a variable. Rho represents all the zeros of the function psi. So it's summed over all zeros of psi, which are the same as the zeros of zeta along the critical line. Okay, so, and we sum it. I won't write this all down, but you have to sum it in a certain order. You take the order of increasing t. So all these zeros lie in this critical strip. So wherever they are, you take them in order of increasing t. And with each one, you'll also have its conjugate. So you take each one, its conjugate, next bigger t, its conjugate. Of course, they're all probably on this line by Riemann hypothesis. But anyway, we sum it in that order. And then you get nice convergence. So very, very simple formula for psi prime of s over psi of s. What do we want? We want the real part of that. So let's just take the real part. And
I'm sorry. This formula is valid only for functions with simple zeros. Yes.
I don't think so.
Okay. Forget it.
Yeah, I think it's valid in general for the entire function. I'm pretty sure it is. But in any case, there is this Hadamard expansion, and if you take its logarithmic derivative, you get just this. And it's valid. I think, I don't know if it's known whether all zeros of zeta are simple, but I think whether or not you have these expansions, I think that's okay. They don't have to be just simple zeros. I can check that. I think not. So let me save you the trouble. If we take the real part of this, let's write a 0 as alpha plus I theta. Then we get summation over rho. And what we get is sigma minus alpha divided by something positive. Just the normal squared, sigma minus alpha squared, plus t minus beta squared. Okay. So the denominator is just the norm squared of the complex number. The difference, it's positive. And what we're interested in is when is this going to be positive? Well, clearly, if sigma is greater than the real part of any 0, this will all be positive terms, and the sum is positive. So, what I can say then, maybe I should write it over here. Well, maybe we don't need this anymore. And by the way, if you, so you look at all these zeros, and do them somewhere, and you can take the sup of the real parts. Let's just call that A. Let it be the supremum of all real parts. So this is going to be greater than 0, as long as sigma is greater than A. A is the supremum of the real parts of all zeros. And we know that A is less than or equal to 1. So, therefore, we get the theorem. Well, I'm trying to prove that. I guess I forgot to write down. I wrote it down monotone decreasing. What I'm going to prove is the symmetric result. Decreasing here is the same as increasing here. So I want to prove that it's monotone increasing over here, and to extend that region is equivalent to Riemann hypothesis. And it's basically done. It's sitting in this formula. If sigma is greater than 1, then all zeros are in this region, so these will all be positive. And therefore, it is monotone increasing. If we have Riemann hypothesis, then all zeros are on this column. This number A that I spoke about is 1/2, and therefore it's also monotone increasing in this region. By the way, also if A is not 1/2, then you can see that it will not be monotone increasing if you get too close to one of these zeros, which was this can become infinitely large negative if you get a little bit less than A. This could be negative, a small negative number, and this could be more or less 0. This could become quite large, negative. So we have proved the theory. Is it okay? Any questions? Everything? So now I will outline what we do in the rest of the paper. I don't want to take too much time, but I'll stop thinking. We prove an inequality. We're interested in the other two functions, the zeta function and the eta function, we can prove the following inequality. That the real part of eta prime of s over eta of s is less than or equal to the real part of zeta prime of s over zeta of s, and that's less than or equal to the real part of sine prime of s, the one we just looked at, over sine of s. So I'll talk a little bit about the proof of this inequality, but I won't go through the whole thing. It will take some time. I'll just outline. But what do we get from this inequality? Well, we just saw that this one is negative up to 0 and up to 1/2 with Riemann hypothesis. So if these are less than or equal to it, they're also negative, and with similar result up to 1/2. So we get the same theorem for zeta and for eta. We find that they're monotone decreasing. Once we have psi, which we just proved, the same is true for eta, for zeta, and for eta. If we can prove these inequalities. So this implies that eta and zeta are monotone decreasing on the region sigma less than 1/2, less than 0, up to here, because psi is decreasing, and to push it further, sigma less than 1/2, totally to the Riemann hypothesis. There's one other technical condition that I should have mentioned, which I forgot, because this is actually false. This inequality, I think, is always true if t is not 0 or a little bit bigger than 0, but this one is actually false for very small values of t. So I should write down here absolute modulus of t greater than 8, which is not a problem at all, only in large values of t. But that inequality would be false if t is too small. So we get this theorem for these two functions with modulus t greater than or equal to 8. With that extra small condition. For psi, you don't need it, but for eta and zeta. It actually will not be monotone if you have too small a value. And you can see that easily from Euler's work. We know that the zeta function is 0 at -2. So the modulus cannot be monotone along with the axis.
So this inequality is supported for negative sigma. But these inequalities are valid for negative sigma. Or
Valid for
Yes, for negative sigma.
for which sigma?
negative, less than 0.
Yes. Aha. So they would be false if sigma gets bigger than that.
And another question. From monotone decreasing of this function, Riemann hypothesis follows. Monotone decreasing of this function implies Riemann hypothesis, but not conversely.
It's equivalent, yes. We can show.
But why equivalent? Maybe something.
We actually prove it both ways. So it's very clear that if it's monotone decreasing, that implies Riemann hypothesis. You cannot have 0. But conversely, Riemann hypothesis implies monotone decreasing. We show it. It's shown in the paper. I think it would take.
If there are, if you have no zeros,
Well, we already showed it for psi. This? Right?
Yes.
And so I have same zeros as zeta.
Yes, I understand.
So I think that will show. The zeros of psi are the same as zeros for zeta. So therefore, if Riemann hypothesis is true, psi is monotone decreasing in here, and that forces zeta and eta also to be decreasing. So it works, it's equivalent. Okay, thanks. It's a nice question. I think that's going to answer it. So, okay, so next question then. How do we prove these inequalities? And I won't go through details, but I'll just outline the general method very roughly. You take the formulas that I did not want to erase. Let's look at eta first. Take logarithmic derivative. So you get eta prime over eta. You first take the log of this. Because this is a product formula, the logarithm becomes very simple. And we'll just get the logarithmic derivative of this part plus zeta prime over zeta. And you can analyze logarithmic derivative of this very easily, and it turns out to be, well, negative in this region. The real part of it. So really, eta prime over eta, take the real part, is the real part of logarithmic derivative of this, which is basically simple, plus the real part of zeta prime over zeta. You can analyze this very easily and show that it's negative in this region. That proves it. The proof for this inequality is similar, but it's longer. It would probably take half an hour to an hour to get details. So I'm just going to outline it very quickly, but we do the same idea. We start from this product for psi, take the logarithm, take logarithmic derivative, and you're going to get logarithmic derivative of s minus 1, which is just 1 over s minus 1. You'll get the Dedekind function. You'll get logarithmic derivative of this plus zeta prime over zeta. And I'll just write out that formula. So here's what you get. Psi prime of s. So it's zeta prime of s. So 1 over s minus 1 is just logarithmic derivative of, where did it go? This guy. Then I get half the logarithmic derivative of gamma, so that's the Dedekind function. Half of it. There should be 1 plus s over 2. Then I get the logarithmic derivative of that exponential, which is really easy. That's just minus 1/2 pi. That's logarithmic derivative of pi to the negative s over 2. So we want to look at the real parts. This one is already real. Here we take the real part of this, real part of this. And we have to take the real part of this one, and it's very easy. We have to take the real part of this gamma. That is a fair bit of work, but it can be handled. There are many known properties of the gamma function. I think I won't go into that part. Let me just tell you that the computation there shows that we can show that Dedekind of So we have some restriction here, but basically what I get is the real part of digamma, I'll call it Z now, is greater than 2, like 2.0408 something, so 2 is good enough. And this will be true for Z is X plus I, Y. We'll use that now. Well, let's say T. T, I'll have to change. And I guess for, well, I'll call it sigma. So it's 1/2 less than sigma, and absolute T would take in greater than 8. That's where that condition comes in. I can bound this digamma function by 2. So basically then, if I go to this inequality, this one, this is very easy to bound. In fact, in this range, it's the absolute value of this would be less than 1/16. Very easy to prove. So what we, and this guy is positive, bigger than 2. This will be relatively small. Minus, is that 1/2 pi or the log of pi? It should be the log of pi, sorry. So I guess you call it P in Europe. In North America, even pi. It should be the log of pi. So this is again a small number. So this is dominating it, and that shows that this sum is positive, which makes this smaller than this, and that proves this inequality, which is what we want. Okay, so just two last things I'd like to say then. A corollary of this, remember that the digamma function was the derivative of the gamma function. So this, I mentioned I had that theorem about monotone increasing of gamma function, and we already get it as a corollary of this, because the real part of the digamma is positive. It's not quite as large a region as in my paper with Zvengrowski. If you just made the estimations a little more carefully for gamma function, you could reduce it from 8 to this 5/4. So it actually comes from this work as well, monotonicity of gamma. So the last thing I wanted to say then, of course, Riemann hypothesis is so famous, and there's been many, many stories about it. Many good stories, many bad stories, many bad papers proving Riemann hypothesis. Every year there's 2 or 3 papers to prove it. Usually they turn out very badly. Anyway, it's probably the most famous problem in mathematics, to find zeros of zeta function. So here is the last part of my presentation. Hope you can see this. It's by, not by me, by Tom Apostel, famous mathematician who works in this field. I guess he's at Caltech. I don't know if I can get all of this. I did a little editing. I think that Apostel is a very excellent mathematician. I don't know if you use his books in any way. They're wonderful. Okay, now we can see it. So, last part of the presentation. It's like a multimedia. A little bit like where are the zeros of zeta of s? George Bernard Riemann has made a good guess. They're all on the critical line, say he, with density 1 over 2 pi log t. Now this statement by Riemann has set off a trigger, and many a good man with him, thin man with vigor, has tried to find with mathematical vigor what happens to zeta as mod t gets bigger. The names are E and Landau, Titchmarsh, and Vermeer. Artie and S and Mentalwood and Ramanujan are there, but in spite of their skill and all their finesse, for finding the zeros there's little success. In 1914, P.H. Hardy did find an infinite number that lie on the line. Too bad that his theorem won't rule out the case. There might be some zeros in some other place. So where are the zeros of zeta of s? We must know exactly, cannot just guess. If we wish to refine the prime number theorem, the path of integration must not get too near him.
Questions? Remarks?
I don't know when that song was written, which year, but I think some people have added further verses based on more discoveries about zeta function. But I haven't.
Who's the original author of this text?
Author of this song is Apostle.
Ah, I see. Yes.
He's a very famous mathematician. I think his original version, I did some editing. I think I improved the poetry a little bit. He's not such a good poet. But some of it is edited by myself, but it's Platonic Apostle.
I want just to add what Peter said, and I forget to tell. So, what use of this inequality? We want to prove monotonicity of any of this function. So now we see which is the easiest, which is more difficult to prove. So it gives indication what is the best way to try to affect the hypothesis by monotonicity.
You could say in Russian.
Other questions? Okay, then.